So far we explained some of the media access control methods that are mostly suitable for fixed network or wired network. The question is, can we apply those ones to the wireless communication? One of the examples is CSMA CD that we mentioned before. It's suitable for wired communication and IEEE 802.3. But some of the problems in the wireless communication doesn't let us use exactly the same method for this type of communication. The first thing is that the signal strength decreases proportional to the square of the distance. That means that the longer the distance, we lose more signal. We are going to lose the strength of the signal anyway, based on the distance between the sender and receiver. The sender would apply carrier sensing and collision detection while the collisions happens at the receiver. So by the time it's receiving the signal, it's not able to detect the collision at this receiver end. It also might be the case that the sender cannot hear the collision, or it might not work if the terminal is hidden. Hidden terminals and exposed terminals are some of the problems in wireless communication. The hidden terminals first. We have a picture here. Imagine if A wants to send to B and C cannot receive A because it's not in the range. C wants to send to B as well. C sends a free medium because it cannot sense A signal. So first of all, the carrier sensing is failed. Collision at B is going to happen, but A is not able to receive it. So collision detection fails in this section as well. Basically, A is hidden from C. The other problem is exposed terminal. B sends to A, and C wants to send to another terminal, not A or B. C has to wait because the carrier sense signal tells the C station that medium is in use. It's not necessary to wait, but because it's sensing the collision, it's sensing the carriers on the utilization, so it's not going to send it and it's going to wait. Basically, C is going to be exposed to B. The near and far terminals are another problem. Signal strength decreases proportional to the square of the distance. We mentioned that before. The signal of terminal B therefore drowns out A signal. So when you're looking at this picture, the B is going to drown the A when they're all sending to C, and C is not able to receive the signal from A. If C, for example, was an arbiter for sending the writes, terminal B would drown out terminal A, and all the signal from B would reach C. Also, there are severe problems for CDMA networks that we are going to talk later on. If you remember, we talked about a static MAC technique called channelization. Basically, FDMA, TDMA, CDMA, and SDMA are different methods of channelization. SDMA is not in the diagram that we had in the early slides of this lecture, but we're going to talk about it briefly here. FDMA, or frequency division multiple access, is basically assigning a subband of a frequency to each user for transmission of data. The channel stays idle if there is no transmission, but it's not going to be assigned to another user. In FDMA, base station and mobile users can send and receive data simultaneously and continuously, and to reduce the adjacent channel interferences, a tight filtering is required. The other one is a time division multiple access, which assigns the fixed sending frequencies to a transmission channel between a sender and a receiver for a certain amount of time. Data transmission is not continuous, but it happens in bursts. And the good thing about this method is the reassigning the time slot can be reassigned based on the priority, and that's why it can provide this or supplies the on-demand bandwidth to different users. SDMA, or Space Division Multiple Access, is a satellite communication mode. It also used on the cell structure. What it does is segments the space into sectors and use the directed antennas property to do that. CDMA, or Code Division Multiple Access, encodes data using the unique code. So basically data before sending the data on the same frequencies, it's adding a code to it, so data are unique when they come to the receiver. Receiver knows how to encode it. It has the code and it can encode the data and take the information. The good thing about CDMA is it can use or utilize the same frequency for all users. Some more detail on CDMA, the access method CDMA. All terminals are sending at the same frequency as we mentioned before, at the same time probably. So the same bandwidth is the whole bandwidth is going to be used. And senders are XORing the unique random number or code to the data before sending it, and the receiver decode that data with the same random number or code it has. The disadvantages of CDMA is it has a higher complexity compared to the other ones. And all signals should have the same strength at the receiver. But advantages is all terminals can use the same frequency with no planning needed, because they're all going to code the data so they can all use the same frequency. There's a huge code space compared to the frequency space, and the interferences or noises are not coded. The forward error correction and encryption can be easily integrated to this system. CDMA is also a spread spectrum multiple access technique that we mentioned in the first lecture. It's basically spreading the signal over the spectrum for better transmission. In this picture you can see an example of FDMA when we divide the frequencies between the senders. While FDMA is dividing the frequency band and assigning the subbands to the users, FDD, or frequency division duplexing, is responsible for uplink and downlink frequency assignment. And it creates a guard band between creating the guard band between the different frequency subbands to mitigate the inter-channel interferences. Since the channels are same frequencies, FDD is suitable for symmetric data, such as voice calls. You can see in this example, each subbands are 200 kHz and the guards are 20 MHz. The traffic from mobile devices to station is uplink, and from a station to mobile devices are downlink. So FDD is responsible to allocate these uplink and downlink frequencies. In TDMA, users are assigned the time slots to send data on the same frequency, and TDD is responsible to allocate the time slots for uplink and downlink. In this example, each time slot is 417 milliseconds. It's obvious that the number of slots reserved for downlink data is greater than the one reserved for uplink. A simple use case is explain this when the browser is requesting for a page. The GET query would hardly be one packet, whereas the response is chunk of data. And TDD is more suitable or used for file transfers. As we mentioned before, the channel efficiency for aloha was 18% and for slotted aloha was 36% or maximum of 37%. But to increase that, we can actually increase this percentage by using the reservation. So we're going to talk about the reservation a bit before starting the rest of the methods that's available on MAC techniques. The reservation can increase efficiency up to 80%. In the reservation system, a sender reserve a future time slot, so it can guarantee that the sender can send the data during that time. Sending within this reserved time slot is possible without any collision, obviously, because it's only reserved for that station. Reservation also causes higher delays because now the reservation procedures need to take place as well. And typical scheme for satellite link using the reservation. Examples of reservation algorithm are explicit reservation or reservation aloha, implicit reservation or PRMA, and reservation with TDMA, and multiple access with collision avoidance or MACA. The first reservation algorithm or method is explicit reservation or reservation aloha. It is also called R aloha. There's two modes in this method. There's an aloha mode for the reservation, or basically unreserved mode, and there's a reserved mode. In the aloha mode or unreserved mode, stations are competing for reservation slots, which are the smaller slots, and collision can happen. But when reserved, there is no problem sending the data, which is the second mode. So in the reserved mode, the time slot is booked for that station, and that station can transmit without collision. It is important for all stations to keep the reservation list consistent at any point of time. That's why the stations have to synchronize regularly. The next one is implicit reservation or packet reservation MA. In this method, there are a certain number of slots that forms a frame. All frames are repeated. A station competes for empty slots according to the slotted aloha principle. Once a station reserves a slot successfully, this slot is automatically assigned to this station in the following frame, as long as the station has data to send. Competition for this slot starts again as soon as the slot is empty in the last frame. So basically, the frame is going to be booked for the data station for the next round, and then whenever it's finished, the station finishes sending, it keeps it only for another round, and then after that, other station can compete for it. The next one is the reservation with TDMA. This is very close to the first one, the or reservation aloha, but this time the mini slots can be reserved as well. So every frame consists of n mini slots, which is shown in the picture with the red part, and x data slots. So these are the data slots. Every station has its own mini slots, so this time they don't need to compete, the station don't need to compete for the mini slots, and can reserve up to k data slots using these mini slots. So x is equal to n times k. So basically in this example, you can see that the mini slots are 6, there are 6 mini slots for each station, and the data slots are 2, or k is equal to 2. And each station can book up to k mini slots. Other stations can send data in unused data slots according to the round-robin sending schema, which is basically the best effort traffic. MACA or collision avoidance, multiple access with collision avoidance, is a collision avoidance algorithm or method that uses the signaling RTS, request to send, and CTS, clear to send messages, and signaling to make sure that no collision is going to happen. So basically, sender sends the RTS or request to send to the receiver, telling the receiver, I'm going to send you a packet, data packet, please keep quiet, you're going to receive a packet, don't send anything yet. If the receiver sends a CTS or clear to send, it basically grants the right to the sender to transmit the data. The signaling packets contains the sender address, receiver address, and packet size. The variants of this method can be found in IEEE 802.11 Distributed Foundation Wireless Media Access Control. MACA is used to overcome the problem in hidden terminals and exposed terminal. If you remember from the example at the beginning of this lecture, in the hidden terminal, A was hidden from C, so they send at the same time and collision happen. Now A and C wants to send to B. A sends a request to send first, and C waits after receiving the CTS from B. So since A sent the RTS first, C needs to wait until the channel is clear and can send the data. Also for the exposed terminals, B wants to send to A and C wants to send to another terminal. Now C does not have to wait, like before when we said it's going to send some signal, so it's going to wait. This time it doesn't need to wait because it cannot receive the CTS from A. And this is the state transition diagram, basically explaining how the acknowledgement for the acknowledgement and negative acknowledgement and receiver busy signals are going through the whole system when the data is traveling using the MACA. If you remember at the beginning of this lecture, we divided the different MAC techniques, and one of them was scheduling under dynamic MAC technique. And in scheduling, we had polling and token passing. In polling mechanism, a central terminal can poll all other terminals according to a certain scheme. For example, if we use the random address polling, base station signals the readiness to all mobile terminals. Terminals ready to send can now transmit a random number without a collision with the help of CDMA and FDMA. The base station now chooses one address for polling from the list of all random number, and the collision only happens if two stations choose the same random number. The base station acknowledges correct packets and continue polling the next terminal. The cycle goes on and starts all over again when it reaches the end of the last terminal in the list. In the token passing, a signal goes through the circle, basically going through the ring of the devices, and it gives the access to each station. In this method, there is no central terminal managing the access granting. And this table is a comparison of different channelization method, SDMA, TDMA, FDMA, and CDMA. You can go through that and compare to see how they are compared together. And basically, what is the advantages and disadvantages of each technique, depending on the system that we are going to use.